Okay, so good afternoon, everyone. Hope everyone is doing okay. So I'm going to start by introducing myself. My name is Farouq. I'm a software engineer at MINDERA, and today we're going to be presenting the Machine Learning 101 workshop that we designed here internally at MINDERA with the help of the other two moderators that we have here on the call. We have Emmanuel Fonseca, who is a product owner here at MINDERA. And we do have Pedro Evangelista, who is a data scientist here at MINDERA too. So quick notes before we get started about this workshop and how it's going to be. So we're going to try to make this workshop as interactive as possible. So feel free to ask questions, whether in the chat or you can even activate your mic and just ask your questions directly. Second note, I pinned the element of a Github repo. You can access it. It's a public repo. And that's where you're going to find all the slides and all the code that we're going to see in this workshop. Keep in mind that this session will be recorded, so even if you miss few minutes or so, we're going to record it and post it later. Another note about the certificates that the attendees asked us about it. So we're going to email the certificates to the people who got the ticket for this workshop, and for the people that came from the general pass, you can just send an email to us and we will send you the certificates. Okay, so we created a poll just to get to know the audience and their backgrounds. So you may click on pools in your screen where you have chat, pools, and people. Just click on the pool and you can answer with your background. This will help us maintain the language during the workshop. Okay. Okay, so enough with administrative stuff. Let's now get started. So the main goal of this workshop is to give you guys some sort of an overview of what is machine learning and how it can be used to solve real-world problems. And as well as we're going to dive into the theory of the concepts behind it. And then we're going to try to turn that theory that we learn and turn it into practice. So let's get started. So the plan of the workshop is going to be the following. We're going to start by defining what is machine learning and what are the concepts behind it. And then we're going to see the types of models and the families and how they are categorized. And then we're going to jump into some examples of certain models. We're going to see the theory behind them, and as well as we're going to see the practice and how we can actually implement them using Python. And then we're going to talk about this very important point that is called bias versus variance trade-off, which is a very crucial point to understand when it comes to training and building these models. And then in the end, we're going to provide you with the learning resources needed so you can dive deeper into each of the points that we are going to talk about today. So the first question, what is machine learning? So before we answer that question, let's now look at how the traditional computer science works in general in the grand scheme of things. So usually in computer science, what you do have at the initial state here, you do have the data, you have the input, and you have this programmer here who's going to write eventually this program that's going to take this data and produces the output, the desired output that you want. So you can take an example here. For example, you want to sort an array or insert an element in an array or any sort of operation you want to do. So you're going to take the input, the array as an input, and the programmer is going to write this program that's going to eventually give you the desired output. This is how computer science basically works in the grand scheme of things. When it comes to machine learning, the way you look at it is a little bit different. So at the initial stage here, you do have the data and you do have the output, but what you don't have is the mapping between the two. So you don't know the pattern that actually matches the two. So you feed this data and output to a certain computer, to a certain machine learning model, and this model is going to figure out that pattern behind it, and it's going to give you eventually that function. So again, computer science is all about taking an X, taking an initial state, writing an f of X, writing that code that's going to give you the Y, that's going to lead you to the Y. Machine learning is having the X and having the Y and feeding it to a certain model, and that model is going to figure out the f of X that's going to map between the two. So when it comes to the fields involved in machine learning and how do they interact with each other. This picture here summarizes all the field that does interact with machine learning in one way or another. So the main ones here are math. So from math we use things like numerical computation, optimization and such. From computer science you use software engineering aspects of it, you use algorithms and all of that. And one thing that we should point out here, that most of the fields mentioned here, they do actually interact bidirectionally with machine learning. So for example, if you take the field of neuroscience, you do have some models in machine learning that are based and inspired by neuroscience and by the brain. And in the same time, you do have neuroscientists that uses machine learning to do their job, to extract useful information from neuroimaging and such. Okay, so this was an overview of what is machine learning. Let's now jump into some definitions of it. So the first formal definition of machine learning came in 1997 by this researcher named Mitchell, where he defined it as machine learning being a computer program A is set to learn from experience E with respect to some class of tasks T and performance measures P. If its performance at the task T, as measured by P, improves by E. So this was a little bit of a complicated definition. So informally, you can just say that machine learning is all about algorithms that improve on a certain task using data. So this is how you look at it at the grand scheme of things. Let's now look at defining those keywords that we talked about in this definition. So we do have the A, the E, and the P, and the T. So let's talk about these in detail in the next slide. So when it comes to the task T and what machine learning can do, this is an example of the tasks that machine learning can eventually tackle. So you do have here a classification and regression, which is just basically when you work with continuous or discrete data. You do have things like machine translation, like Google Translate, for example. I mean, a lot of people take Google Translate as being, something easy. You just set a word, click OK, and you get your translation. But in fact, behind that click, there is a long history of theoretical research in natural language processing and machine learning. You do have things like structuring the input and structuring the data. So, for example, you cannot just, it's not just using machine learning to make the final decision. You can eventually use machine learning to just structure the data. So, a human can get the insights from it, can get a better insights from it. You have things like anomaly detection, synthesis and sampling, imputation of missing values, denoising. This is a very important one. And you do have unsupervised things like clustering, for example. So this is what machine learning can do. Let's now look at the experience, the E that we talked about. So this can be represented as the data that you do collect eventually and how you can feed it to these machine learning models. So the data can come in these three main forms. So you do have the first case, which is the supervised way, which you have, as we said in the first slide, you have the X and you have the Y, and you're gonna wanna figure out the pattern between the two. You do have the unsupervised way, which is you do have basically just the X in your data and you don't know where you want to go. And this is an example, a good example for this will be the clustering algorithms, where you do have just the X's and you want to figure out some clusters and certain patterns in that data. And you do have this third form, which is called reinforcement learning, and which is basically the study of agents and intelligent agents. And the data in this case can come in the form of model dynamics. So imagine you are trying to train an intelligent agent to play chess or a certain game. You're gonna either you feed it the model dynamics of how this game works and the agent can eventually learn, or you can feed it, for example, the episodes of examples of this game being played, and the agents can learn from those episodes. We talked about the P. So the P is basically the performance of the model. You can use, for example, the accuracy, which is how many things this agent is getting it right. There is the loss, which is basically the error, and you have the recall. So let's now talk about the fourth piece of that definition, which is the model, the computer program that we talked about. So when it comes to building models and designing these models, it always comes down into these five main components of it. So the first one we can see here is called the architecture or the baseline. So this is that first initial function that you're gonna start by. So For example, if you plot your data and your data looks linear, you're just gonna use a linear model as a baseline. You're gonna use just the the simple equation of a linear model to eventually solve the problem. There is the second component, which is the objective function, or the loss function it is called. So this is how you define. So once you start with that baseline model, the objective function is gonna mathematically define how you can solve how you can arrive to that y, the desired y that you want to arrive to. And this is very important, because even if you have the correct baseline and you don't know how to express your problem mathematically and set it as an objective function, you can't actually build these models. And then we have the third component, which is the optimizer, and this is also a very crucial component of the model, which is once you define that baseline and once you define how do you want to go to that y, to that desired output, you're going to use the optimizer to optimize the baseline so it can eventually arrive at that desired output. We do have the evaluation metric, so this is basically how we can evaluate our model. So basically your model is going to learn to do something, and the way you evaluate this learning is actually really important too. And you do have the regularizer. This is also an important term. So the regularizer, for now, let's keep it as being something, a certain term that we add in our model to prevent the overlearning, because we always want our models just to learn the right way. We don't want our models to overlearn things. Okay, let's go to the next slide. So this is an example of the very first, very simple machine learning models, which is called linear regression model. And we're going to apply it on a very famous data set called the housing price prediction, which is basically looks like this, the data. So you do have the size of the house, you do have number of bedrooms in the house, and the y that you want to arrive at is the price of the house. So that's how you can predict you're going to predict the price of the house based on one of these features, all the features if you want. So in our case, in the example that we're going to show, we are just taking the size of the house, and we're going to eventually predict the price of it using this linear regression model. So if you plot our data, it will look something like this. So we put the size here in the x-axis, and we have the price in the y-axis. And the goal of the machine learning is to arrive at this linear function here, that it is perfectly matching this data. So when it comes to, so we've seen that we want to arrive here. So how we do arrive here is by defining the components that we talked about before. So let's try to define them now. So we always said that it comes always to these 5 main components of every model. So for the baseline, as we saw after plotting the data, it looks like a linear data. So what we're going to do is to define the model, define the hypothesis as being linear. So it's going to have theta 0 plus theta 1 plus multiplied by x. So theta 1 is basically the slope of the function, and theta 0 is the intercept of the function, of the baseline. And when it comes to the objective function, to semantically and mathematically define how you want to approach that data, we're going to use something called the mean square errors, which is basically defines the Euclidean distance. So imagine you define your baseline. So imagine you define your baseline as being 0 slope and 0 intercept. So it's going to be basically here. And the mean square error, what's going to show is basically the mean distances between each data point here and our baseline. And that's how we define our objective function. So that's basically what this term is saying. So this is the mean of the y minus the predicted y. When it comes to optimizing, so how we can eventually reduce that distance and get to where we want to get, we're going to use an optimizer, very popular optimizer called Gradient Descent. We're going to talk about it in details in the next 2 slides, but the main rule, or the main thing about Gradient Descent is basically this: it's going to optimize the parameters, so each parameter. So if you take theta 0, it's going to be theta 0 equal to the previous theta 0 minus a certain alpha multiplied by the partial derivative of the mean square error with respect to that theta 0 that we are at. And we're going to explore this in the next 2 slides. Just keep it in mind like this. For the evaluation metric and how we can evaluate this model, we're going to use the accuracy, which is basically how many data points the user is going to get right. And for the regularizers, just keep in mind that one of the popular regularizers that you can use in linear regression is called the L2 norm. So let's talk now about gradient descent. So we defined this optimizer. Let's now talk about it in a little bit more details. So the basic intuition behind gradient descent and how it works, basically, you can plot it as this. So once you define that mean square error, once you define that function of the distances between the data points and the baseline, and you plot it, it's gonna look something like this. So this is the cost with respect to the weights that we have. And what gradient descent does, basically, you can imagine it as being this ball here. So your parameters are going to be initialized here, and gradient descent is going to iterate to get to the minimum cost possible. So that's what we want to do in linear regression model. We're going to basically just try to reduce that distance between our baseline and the desired function that we want to get. So the algorithm is going to get to the minimum here by using this rule that we talked about. So basically, you set theta 0 here, and you make a minus alpha multiplied by the partial derivative of this function that we are plotting with respect to that dimension, to that parameters that we are optimizing. And the partial derivative here basically define the slope of the function. So as you can see in this line here, so the partial derivative at this point is the slope. And we're going to take the negative slope, so we can eventually go down. But if you want to go up, you can just take the slope as well. So, and we do have this alpha in the equation that we didn't talk about. This alpha is called the learning rate, or is called the step size, and which is basically defines how fast we want to move into this function so we can arrive at the minimum. And an intuitive question here would be, so if this is the step size, so why we won't just set it high and the ball here will converge very fast to get to the minimum. And this is actually one of the problems in gradient descent, where if you set this alpha too high, your model is gonna overshoot this minimum, and it's gonna keep overshooting, and it will never converge. And on the other hand, if you set the alpha too small, your algorithm will also never converge, because it will keep like moving very slowly here to arrive to the minimum. So this was the basic intuition behind gradient descent. Let's now talk about some of the problems that gradient descent faces. So at the left side here, you can see that this looks like the function that we saw before, which is called, you can call it as being a convex function. A convex function is basically a function that has one minimum. And that's why we use gradient descent. So you're going to initialize this ball here and run it, and it's going to iterate, keep iterating till it arrives at the minimum. But a lot of machine learning problems, when you plot their objective function or their loss function, it's going to look like a lot like this, as being known as the non-convex function. And a non-convex function, basically, it's a function that does have a lot of minimums. So you can see that you have the local minimum here, and you have the global minimum here. So if we initialize our gradient descent here and it keep iterating, it will be stuck here at the local minimum, and it won't converge to the global point that we want to arrive at. So this is actually one of the very valid critiques that people give to machine learning, where they say that basically in machine learning you're just solving problems locally and not globally due to the limitation of this optimization problem that we are talking about. But well, when it comes, so theoretically, you can say that machine learning is limited due to this optimization problem. But when it comes to practice, actually, even if this local minimum actually, give you what you want, actually, it does solve your problem eventually, and you don't have to get this global minimum. So now, after seeing these different components of linear regression, let's now look at some code and how it is implemented using Python. Before we jump into the code, is there any question up until now about the content that we just talked about? Do we have any questions, Emmanuel? Okay. All right, so let's go. So when it comes to the code and how we can implement linear regression, we are implementing it to solve the housing price, as we said before, and the code is gonna be implemented in Python. So let's start here first by, oops, sorry. So let's start by importing our library first. So we're going to use NumPy for numerical computation in Python. We have Panda, which is basically a library that helps you in reading the data and pre-process it. And we do have matplotlib, which is basically a library that helps you with the plotting. So let's first run this piece of code so we can import our libraries. And here, this is basically Google Drive, so we can import the data from my drive. Okay. Okay, this is basically, we call panda.readCSV because our data is in CSV format, and we're gonna read the housing price CSV file. And once we print it, this is how it looks like. So we have the X as being the size of the house, and we have the Y as being the price of the house eventually. And our goal is to figure out the pattern between the two. So when we plot our data, it looks something like this. You know, X giving the Y, and the goal is to build a model that's gonna fit the data here. So let's start by defining the components that we talked about in the slide. So since this data, after plotting it, it looks a lot like a linear model, so you're gonna define your function as being m, the slope, multiplied by x plus the intercept. And you're gonna define this hyperparameter, so the learning rate, the alpha of gradient descent that we talked about. And actually in practice, this value here, there are some fancy ways to define it, but for our case, I just tried multiple values, and this one seemed to work best for us. We're gonna define the initial b and initial m as being 0 and 0, and the number of iteration, which is how many iterations we're gonna train this model on our data. So let's run this piece of code. So this was the baseline of the model. When it comes to the loss function, or the cost function as we called it, it's gonna be a function that takes the parameters as an inputs, and it's gonna take the data, so the initial parameters and our data where we want to get. And basically what it's gonna do is basically loop through the data points. So that's what we are doing here. So loop through all the data points, read the current data point, the x and y, and calculate the Euclidean distance between the two. So basically y minus the y that we are predicting, that random guess we are making with the baseline, squared. So this is the mean square error that we talked about. And in the end, we're gonna just return the mean of it, so the mean of the square errors. So when it comes to gradient descent and how it works, so basically gradient descent is a function that's gonna take the b current and the m current slope and current intercept. It's gonna take the data points that we have, and it's gonna take the learning rate, the alpha. So we first start by defining these gradients, its slopes that we talked about. This is basically the n, the number of data points, and we're gonna loop through all the data points, and we're gonna eventually read x and y of the current data point, and we calculate the gradient using that partial derivative that we talked about. So this is represent the slopes of the cost function with respect to b. And for the m, the same thing. So this is the partial derivative of the cost function with respect to the m. And after we calculate those gradients, after we accumulate them, as we saw we are doing here, we are accumulating the gradient for each parameter, we're going to use this update rule that we talked about. So we're going to say the new b, and that's how we are iterating, is equal to the current b that we are at, minus the learning rate multiplied by the gradient, by that slope that we defined here. And the same thing we're gonna do to the m, and that's what learning is all about. Is about updating these parameters until you eventually converge the actual solution. So let's run this piece of code. Okay, so these are basically were the components, and when you try to train your model, you're basically gonna define the b and the m as being the initial ones, and you're gonna loop through the number of iteration that we defined and run gradient descent and keep accumulating the b and the m. And here we are basically just plotting the number of iterations and the error after that. So let's run it. It's gonna be very fast. Okay, so after 1000 iteration, the b was equal to 0.8 instead of 0, because we did start by 0, and the m basically is 147. So it mapped from the 0 to 147. And once we plot these parameters that we have, this is what we get basically. We have this straight line here that's fitting the data. So this proves that our model, the linear regression model, actually learned to predict the x giving the y. Okay, so I just want to show you this visualization of the optimization process. So this is basically how it looks like dynamically. So your model is going to start here at the baseline, and as we iterate, it keep changing its parameters until it finally touches the data. And the second link here is basically the cost function is 3-dimensional, because in the slide we saw it just in 2 dimensions. So it was the cost with respect to the first parameter, but since our model has 2 parameters, the m and the b, this is how the cost function looks like. So let's now get back to our slide. So do we have any questions up until now before we jump into the types of models? We have a question here. I think it says we have the question, what is the complexity of machine learning algorithms? Yeah, this is actually a good question, because since we are calling them algorithms, in the analysis of algorithms in computer science, you always have this thing that is called the complexity, which is basically defines how complex your solution is going to be when you try to solve a certain problems. But one thing that we should point out here is that, let's go to the first slide here. So in computer science, so when you have the data as an input and you write an algorithm that has a certain complexity, has an upper bound and a lower bound in the complexity, each time you're gonna get a new input and execute this program, it's gonna eventually take that amount of time, take that amount of complexity. But in machine learning, it differs a bit. So even your model, even the complexity of your model, let's say it's exponential, but once you train this model, and it's gonna take, for example, an hour or half a day or whatever, but once it's trained and you try to use it, it's not going to take the same complexity. It's just going to be a matter of seconds of inferring that variable. And that's why you don't find a lot of people talking about complexity when it comes to machine learning, because once you make the inference, it's not going to take the same time. Yep. Yeah, that's a very good point, actually. Yeah, that's a very good point you added, actually, Pedro, because I think this picture can explain it too. So if you run your algorithm for 100 iteration, let's say, and it arrived at this perfect line, if you run it for 1,000 iteration, if you keep running it, it will eventually miss this fitting, and it's gonna get actually a poor result. So the number of epoch and the number of iteration you run your algorithm on is actually very crucial here too. Okay, can we move on to the next point? So there is someone that asked about the setup of this workshop. So basically, you have a GitHub repo which is pinned in the chat, you can just access that repo and go to Google Colab, where you can import those Jupyter notebooks, and you can eventually run the code and play with it. But if you have any issues with running that, please let me know. Okay, let's jump now to the next point of the workshop, next part. So here we're going to talk about the type of models and the families of the models and how they are categorized, basically. Sorry. Let's put it into full screen. So when it comes to the families or the tribes of machine learning models, this picture here summarizes the tribes that the machine learning hinges on, basically. So let's start by talking about each one of them. So let's start by the first tribe, which is called the symbolicist, or it is also known as being the symbolic AI. And this is basically what this tribe says is basically they say that intelligence can be reduced into manipulating symbols the way mathematicians do. So you have certain equations and you're going to manipulate its symbols, so you're going to eventually arrive at solving problems and solving intelligence. And they also do believe that the learning cannot happen from scratch. So you cannot learn just from data. You need to have these basic symbols or the basic rules, and then you can put data on the top of it, and then you can eventually arrive at the learning. And one of their popular models, and this tribe basically worked maybe from the 50s until the 70s, I would say. And one of their popular models at that time was called the expert system, which is basically a giant networks that contain rules. So as we said, this tribe believes in rules, so the world around us should be formed in rules. And what the expert system do basically is a giant system that has rules, and you're going to send data to it, and it's going to figure out the output of that data based on those rules that you define. And basically the first version of this theory was rejected around the 70s for being completely unscalable. So you basically cannot encode the whole world or the whole intelligence as being rules, because there are a lot of uncertainties in the world due to the incomplete observations and such. So you cannot modelize everything in rules, basically. And this is actually what, after the rejection of this idea, this is what started what is known as the AI winter, which lasted from the 70s until the mid 80s, basically. And during these 15 years, basically, not a lot of people actually were trying to, solve intelligence and build these intelligence systems, because they thought that, okay, if the symbolicist hinged on this idea and it failed, then there's no way further. But eventually, people came up to it and they built an amazing models that we have today. So this was the first tribe, the symbolicist. So let's now talk about the connectionists. So the idea behind the connectionists is basically learning is all about the brain. That's what they say. So they say that we are human beings and we do have this amazing machinery, which is our brain. And we need first to understand how the brain works, and that's how we can eventually derive intelligence and build intelligence from it. And the way the brain works, so let's try to get into some details. The way the brain works, actually, our brain has these things that are called neurons. And learning is all about, forming synapses between these different neurons, or forming parameters between these different neurons. And this is the tribe that actually gave the rise for the artificial neural networks. So this was the connectionist. So learning is all about the brain. And then we have this tribe here, which is called the evolutionaries, where the idea here hinges on the theory of evolution. So they say that, okay, if learning is all about the brain, then let's take a step back. The brain didn't just happen to exist. The brain did evolve during the time. So we need to figure out, a way to modelize that evolution, and that's how we can eventually arrive at the intelligence. So they believe in evolving the structure of learning. So it doesn't matter, like you're gonna start with a basic baseline, and you're gonna, write an algorithm that's gonna evolve this baseline to arrive at the desired model that we want. And this is the tribe that gave algorithms like genetic programming and genetic algorithms. So this was the third tribe. When we jumped into this tribe here, so the Bayesians, And Bayesians, the naming come from the Bayes theorem, which is one of the very popular theorems in probability theory. And basically, Bayesians are concerned with all the issues that we mentioned before in these tribes, but they do believe in uncertainty too. So they do believe that the world around us is full of uncertainties. So we need to figure out, to build models, how to modelize that uncertainty and manipulate it, and that's how we can build intelligence. So it's all about, modelizing these uncertainties without falling apart. Yeah, just one point I want to add about the Bayesians, about the uncertainties, and this is actually a very important point. So the uncertainties that we have in the world basically come from 3 different sources. So you can have uncertainties on the phenomena that you're observing due to the incomplete observation. So imagine, I don't know, you're trying to predict the weather or something, and you don't have the full observations of this phenomena. So that's eventually how you cannot predict the weather accurately. There's another type of source of uncertainty, which is the incomplete modeling. So basically, you're looking at certain phenomena, but you're not taking all the variables of it to make the prediction. Another source of uncertainty would be the model, the dynamic transition, I would call it. So it is basically when you, for example, you train a certain model as predicting weather in the winter, let's say, and then the phenomena that you're observing transition to, let's say, winter, which is the phenomena is going to change completely. So your model won't be able to predict at this new model transition. So this was the idea behind the Bayesians. So it's all about uncertainties. And when it comes to this tribe called the analogers, analogers basically come from the word analogy, which is basically can be defined as being abstractions. So they do say that the key of learning is all about recognizing similarities between the contexts. So for example, if you take an example, you have 2 patients that have the same symptoms, let's say for a certain disease. The key here is to decide how similar those 2 contexts to. So their models basically, they have to to perform better in a certain context, and if you want to change it to another context, you're just going to make the abstraction, make the analogy, and you're going to go to the second context, and your model have to perform in the same way. So this was the last tribe. So I want to add two main points to all the things that we talked about here. So I would say that the main takeaway from this slide is you have to realize that there exist these different categories, different families of models, and all of them basically do hinge on a very solid scientific intuition. So we should not qualify or disqualify scientific methods based on their engineering success. So we all know that the connectionists that gave the artificial neural networks are trendy now, but that doesn't mean that this is the singularity. That doesn't mean that we should pursue science only in this way, because they are giving their models tend to have a lot of impact in the industry. Because at a certain time in time, symbolicists thought that they were the ones that solving intelligence, and then they basically faced the wall. And you have to keep in mind too that it's good to look at them at the model as these different families, but keep in mind that in practice they do actually overlap between each other. They do, and even during the course of history, they did co-evolve between each other, and you find yourself using a component from this family and use it in another family, and so on. A good example would be, for example, building artificial neural networks and train it using an evolutionary algorithm. And this is perfectly a valid example for the co-evolvement between these models. So let's now look at just this table is going to basically summarize what we just said. So the symbolicist is all about the structured inference or the deterministic inference. Their technologies are basically the production rule system and the inverse deduction. When it comes to the connectionists, so their strength is basically estimating parameters. So it's all about forming those synapses between the different neurons, and that's what learning is all about. Their technologies is basically deep learning and backpropagation. We do have the Bayesians, and their strength is you can call it the weighing evidence, or you can call it probabilistic inference. So instead of structured inference here, you're going to do probabilistic inference. So you have different evidence, you're going to give weights to each one of them, and that's how you can eventually make your decision. their technologies, they basically gave models like graphical models and hidden Markov chains, which are basically probabilistic models that can be used to modelize stochastic processes. You have the evolutionaries, basically the structural learning, so evolve models in order to get a better learning structure. So example for this is genetic algorithms and evolutionaries, evolution programming. Analogous, you have mapping to novelty, and one of their popular models was the KNN, K-nearest neighbor, and we do have the support vector machine. So in the scope of this workshop, we're not going to tackle each one of them due to the limiting timing we have. So we're going to see we've seen the linear regression model, and we're going to see the neural network here. So do we have any questions before we jump into the next point? Yeah, sure. Let me read it. Yeah. It's a good one that you mentioned about the historical context of artificial neural network. That's actually a good point, because a lot of people think that since neural network are taking the edge in the last few years, they think that the theory behind them is also new. But in fact, the word of artificial neural network occurred in academia around the 1950s. And they were limited due to some optimization problems and due to many problems. And they did actually, take the edge in the last 10, 20 years because of the computation that we have now and the amount of data that we do have now. So do we have any other questions? So before we jump to the next model, I will make maybe 5 minutes to Q&A. Anyone who wants to ask a question, please go ahead. Okay, let's a few more seconds and we shall start. Okay, we have no question now from Victoria Buzak. So going back, the question was going back to talking about the brain. What's the difference between human intelligence versus artificial intelligence currently? So the answer for that question, I would say that artificial intelligence currently is good at targeting disentangled, isolated problems. So if you want to solve weather prediction, or you want to solve a certain classification problem, artificial intelligence is actually very good at that, and in a certain task, even the human brain won't be able to solve the problem as good as it. But when it comes to the high-level cognition and what the human brain can do in general, in the grand scheme of things, that's actually when it occurs the difference. So artificial intelligence basically is now trying to solve the perception problem. So the perception that we have as a human being. So we collect data through our eyes, auditory, kinesthetic, and such, and we make decisions based on that. That's the current state of artificial neural networks. But when it comes to the cognition and how you can scale these systems, that's actually still an active area of research, and we haven't seen a lot of progress in it. I hope that answered the questions. Thank you. So if we have no more questions, we can just move on to the next point. Okay, let's move on. Yep. Okay, let's move on. All right, so the next point that we're going to talk about is we're going to dive into the theory and the implementation of the artificial neural networks. So let's get started. Okay. So this slide shows basically the basic intuition behind artificial neural networks. So you have this picture here that visualize the artificial neural networks and how they look like. So the key observations about this image here is first the layer based that we can see. So we do have an input layer, a hidden layer, and an output layer. And this actually can change. You can have multiple layers as well. So the first key observation about this image is the layer structure of this artificial neural networks. The second observation will be the composite functions. So you do have this neurons, these nodes here, which each one of them is going to hold a certain function, a certain nonlinearity. And these functions are going to be composed together so they can form this giant function, this artificial neural networks that gonna solve the problem for us. And you can look at artificial neural networks as being this this giant function that gonna take a certain input and produces the output. Another observations, as we said before, so the weighted neurons, so is the synapse basically. So how does each neuron connect with the other? And this actually what represents the parameter that we mentioned in linear regression. So in linear regression, you just have two parameters, which are basically the slope and the intercept. In the artificial neural networks, you do have these connections, which each one of them represents a parameter that we're gonna eventually optimize. Another observation, which is the two pathways. So you can see that your model is going forward and backward. So during the training, you're gonna see this both paths. So your model is gonna make a random guess, and then we calculate the difference between the random guess and the actual truth. And then we're gonna work our way backward to optimize this synapse, to optimize these parameters that we have. So this was the basic intuition behind the artificial neural networks. Let's now look at the similarities and the differences between these two models. So when it comes to similarities between the artificial neural networks and the biological neurons, as you can see here, the biological neurons have basically this cell body, so they are basically just the cells that shaped in different ways. They do have the axons, which are basically channels that are going to send informations, and you do have synapses that we talked about, which are basically a way to connect with other neurons. So you can see that the structure is similar a bit to the artificial ones. So key observations about the similarities: we do have the two pathways, which is there's this phenomena that happens in the brain called the neural plasticity, which is basically a phenomena. It's a mind state in our brain that happens, which our brain will be optimized to changing those synapses between the different neurons and eventually do the learning. In both artificial and biological, we do have the composite functions. So we do have these small neurons at the unitary level. They are all the same, but the way that they connect and the way you combine them, that's actually what makes the difference for the learning. They are both oriented by data and not architecture. So as we saw, composite functions are all the same, but for example, this actually was an experiment that was done in the University of Manchester, where what they did basically, they took a mice and they inversed the auditory cortex in their brain with the visual cortex. And what they noticed is that the visual cortex, which is meant to treat images, when they connect it with the auditory sensors, they found that it is getting trained to solve visual problems. And it's actually proof that says that the neurons at the basic level, they are all the same, but the data that you feed them actually matters. And we do have the hierarchy of representation. So as you have deep neural networks, each layer is going to contain a certain level of representation, a certain level of abstraction. So these were the similarities. Let's now look at the differences between the two. So when it comes to signals and how the neurons communicate between each other, this is actually very different. So the artificial neurons basically are these programs that we are building, and they are getting run on a computer. So they are getting run on basic silicon and transistors. So the signals that are sent between the neurons are basically electricity. But When it comes to biological neurons, they do actually send signals and send data in different ways, where in the brain you have these chemicals that are called the neurotransmitters, and that's what actually take the data between the different neurons. When it comes to the frequency of firing, so how many times the certain neuron fires, actually you notice that the biological neurons are actually very slow compared to the artificial ones. But one thing we should point out here, that being slow does not mean that it is less performant. So the biological neurons do fire less, but they are way optimal than the artificial neural networks. So when it comes to the topology and how are we connecting these different neurons, so as we saw in the previous slide, we saw that each neuron from a certain layer, so the input layer, is connected with every neuron in the next layer, and this is what is known as the fully connected layers network. But when it comes to the biological neuron, this is actually a mystery. So neuroscientists haven't figured out, what is the topology in the human brain. So you find neurons, forming connection with different neurons, and this is totally a mystery in the human brain. When it comes to the power consumption, so our brain consumes about 20 watts to operate. And when you go to the artificial neural networks, and then when you train them on GPUs and CPUs, they do consume about 250 watts. So they are very computationally expensive, actually. And the last and the main difference is the learning or the optimization. So neuroscientists did observe this phenomena that is called the neuroplasticity, which is basically when the brain is learning, but they don't have clear formulas and clear equations on how this learning is working, how we can modelize this learning mathematically, and this is still a mystery, actually. So the main takeaway from this slide, guys, as we saw the similarities and the differences between the two architectures, the main takeaway here is that you shouldn't say that the artificial neural networks are based on the brain or are built on the top of the brain. That's actually kind of wrong to say. So a right way to describe them as being the artificial neural networks are just a mathematical representation of what we have understood from the brain. But there are a lot of things that we do not understand about the brain. So that's kind of like wrong to say that we are mimicking the brain, because it's something that we don't actually understand. So now let me just show you some motivation behind the neural network, the artificial ones. So this picture basically summarizes the performance in respect to the amount of data for all the models of machine learning and deep learning. So you do have here the traditional learning algorithms like linear regression, SVMs, polynomial regression, and such. And as the data grow during the time and during the last 10-20 years, these traditional learning models, actually tend to be very limited and unscalable. And that's why actually the neural networks are actually very performant than the others. So when you give a neural network more data, it's going to actually be more performant. And as you grow in the structure of the network, it's actually going to be even more performant. So that's why the neural network are beating the other models due to this layer-based and composite-based structure. It's actually outperforms the others. So this was an overview of what are artificial neural networks and how they work. So let's now break them down into the different components that we talked about in the linear regression. So when it comes to implementing these neural networks, the baseline or the architecture, we saw that it's already defined. So we do have this composite structure, and we do have these neurons and these connections and such. So if you want to define the baseline of your artificial network, you're basically going to define the number of neurons, the number of layers, and the activation function. So you're going to define how many abstractions you want to have, how many layers, number of neurons in each layer, and the activation function. And this is something that we didn't talk about in detail, but the activation function is basically an example of a non-linear function. So you're going to put into the neurons, and when you combine these non-linearities, they will be able to approximate any other functions that you want to approximate. So when it comes to objective function, how we can actually start from this baseline to arrive to our solution, we're going to use another type of objective functions called the cross entropy, which is basically a measure. So we saw the mean square error before, which is a Euclidean distance. The cross entropy is a measure that represents a distance between probability distributions. So, instead of taking that Euclidean distance, now we're going to take a distance between probability distributions. And you can also use other measures of probability distributions like the Chi-L divergence or the Wittgenstein distance and such. So when it comes to optimizing these neural networks, we're going to use gradient descent to optimize its loss function, but we're going to combine it with something called backpropagation. And this is actually a very interesting algorithm, which, as we said, the artificial neural networks existed from the 50s, but before the discovery or before the invention of backpropagation, actually they were quite limited when it comes to optimizing them. So this algorithm was discovered around the 1986, if I do recall. It was discovered by Geoffrey Hinton and Williams, which are one of the main figures when it comes to deep learning. So what this algorithm basically does, that it uses the chain rule. So the chain rule is a math concept that's tells you how to calculate derivatives when it comes to complex functions like neural networks. And you're going to use this chain rule to eventually calculate that gradient and backpropagate it through the network to update your parameters. And that's why it's called backpropagating. So you're going to take the gradient and backpropagate it through the network. So when it comes to evaluation metric, we're just going to take the accuracy, so how many predictions this network is going to make right. And for the regularizers, you can use the L2 norm, the same one that we used in linear regression. And you can use as well, actually, the a very interesting technique called the dropout. It was discovered by Yann LeCun in 1998. And which is basically this, we said that the regularizers prevent us from the overlearning, or the overlearning that we talked about. And the dropout, what basically does is during the training, it turns off the different neurons at random times. So you would allow your network, to use all of its neurons instead of being, focusing in certain pathways during that training of the neural network. Okay, let's now jump into the code and the implementation of these artificial neural networks. So before we jump into the code, do we have any questions, thoughts, opinions? Okay, if you guys want to ask any question, you can just activate your mic. Okay. Can you ask the question, Emmanuel? I think I didn't hear you. Okay, good question. Good question. Yeah. So AI does have threats, but not like the people think about. So you do have. So people, when they think about threats of AI, they think about the scenario of Terminator 3. So where basically machines are going to be self-aware one day and they're going to eventually decide to destroy us all. But the current threat of AI, we are not there yet. But the current threat of AI comes from human themselves. So I mean, people can use AI to build weapons or to build, I don't know, mass destruction weapons instead of building useful things, So the threat of AI currently is due to the humans and not due to the AI itself. So that's the main answer for this question for me. And this threat actually exists in any novelty or any invention of human beings. If you take, I don't know, basic invention of human beings can be used in a two-way, is a two-edged sword basically. You can use it to create useful things, or you can do evil things by it. Let me just enter the chat because I can see the Is the regularizer good for overfitting? Yes, definitely. That's actually one of the main goals where we use the regularizers, because as we said, like if you run your algorithm for too many iterations that it's needed, your model is gonna overfit to that data that it's seen, and it won't able to generalize to a new data set, a new novel data set. And that's why you definitely always need to put a regularizer in your model so you can eventually learn things, learn them the right way. Yeah, yeah, definitely, definitely. Any other questions? Yeah, he said, Riyadh said, AI is a coin of two faces. It depends on how we use it. It's definitely, that's exactly what I said. So you can use it in both ways. Use it to do useful, meaningful things to the human species, or you can use it to do evil things. And that's on you, not on AI. Yeah. Yeah, that's actually a very valid point where AI basically and machine learning hinges on data basically. So if you don't have data of these phenomena that you are trying to solve, you won't be able to use machine learning. And as we've seen the scandals that happened during the past years between Cambridge Analytica and Facebook, where they exposed private data of the users to certain research labs, and that's actually that's actually one of the threats that we have in machine learning community. So, but there are some people. For example, I can give you an example of OpenAI. Andrew Trask, the director of OpenAI, is working exactly on this point on how you can train these models without explicitly giving them the data. For example, if you have medical data and it is very sensitive, they are working on certain models, like encrypting data and such, and you train these models on, without explicitly giving it the data. So yeah, that's perfectly like valid point, and people are working on trying to solve it. Yeah, yeah, yeah. We do have this thing that is called reverse engineering in all the fields of engineering, and people actually did it in artificial neural networks. So you train a model on a certain data, and they reverse engineer from that model that is trained. They reverse engineers the data, and they violated the privacy of a certain users. Yeah, yeah, that's perfectly actually a very valid point that you mentioned, Pedro. Where I mean, even the human intelligence, even the humans with this amazing machinery that it is our brain, we are exposed to that problem. So, if the human brain is exposed only on a certain type of data, and it's never seen that change before in any other forms, it won't be able to generalize to that new problem. So yeah, that's actually an issue that happens even with the human intelligence and not just the artificial ones. So if we have any further questions, let's now jump into the implementation of the neural networks. So all of the code of this workshop, guys, is in the GitHub repo that I put on the chat. It's pinned. So you can, download the repo and import the code in a Google Colab app, and you can eventually execute the code and play with it. So we're gonna try to implement neural networks to try to solve what is called the handwritten digits classification. So you have certain digits that are written by hand, and we're gonna train this network so it will eventually, take that image and predicts what's the number that it is on this image. So we start basically by, let me just zoom in a bit. So we start basically by importing our libraries that we imported before. So NumPy for numerical computation, Panda for the data, and Matplotlib for the plotting. Let's run this piece of code first. Okay, authorization. Okay, we imported. So this is what we are going trying to build. So we will build this neural network that has an input layer which contains the features of the data that we're gonna feed, and we have one hidden layer which is gonna consist of 100 neuron, and we have an output layer which consists to the Ys that we want to arrive at. So we have 10 because we are working on handwritten digits, so they are 10 digits from 0 to 10, and that's corresponds to the 10 outputs that we have. So let's first load our data set from the drive that I have and print its columns and rows. So our data consists of 40,000 images, and it has 785 features. So we saw in the linear regression and the house prediction problem, we had just one feature, which was the size of the house. But in this case, we do have like a lot of features, with more than 700 features. And the label, we have just one label per each image. So each image is going to have one number in it inside. And now what we're going to do here is basically split our data into training and testing set. And this is something we didn't do in linear regression because it was very simple. So when you train and build these models, you want to always split your data. So at the time, if you want to test your data and test the performance of your model, you're going to give it novel data, new thing that he didn't see before. And that's how you can ensure that your model is actually learning and not just memorizing those patterns. So this is basically what we are doing: reading the data, reading the labels, splitting them. And in here in this line, basically what we are doing, we are converting the images to being a binary images. So they're going to be just black and white instead of the full RGB color that usually exists on. So let's run this. And now we're going to plot our images using Matplotlib. So this is how, just a sample from our images and how they do look like. So, I mean, using our visual cortex, the human visual cortex can easily identify this as being all fours. But how you can actually, build a certain model that gonna, without any explicit rules, know that each one of these are an actual fours. So that's what the neural network is gonna solve for us now. We're gonna apply this one hot encoding. This is basically converting each label. So for example, if you have a 0, you're going to convert it to a matrix that's going to contain one just at the index with number 0, and eventually you're going to do all for the same. And this is actually, it turns out to be a very good practice when it comes to the classification training, and that's what we are trying to do. Because you're kind of bounding the training, you're giving boundaries to the network to search in a certain space, and that's what the one hot encoding stands for. Okay, this is we already seen. Just a second. Okay. So let's now start by defining those different components of the model that we talked about. So we're going to use two types of activation functions. So usually in most of the models you do just use one, but in this case we're going to use two. So we're going to use the ReLU, which is a nonlinear function, and we do need its derivative too, so the ReLU prime. And we do have the sigmoid and its derivative too. And usually in the first implementations of neural networks, people just use the sigmoid and its derivative. But it turns out that the sigmoid actually, as we're going to see, have a problem in its derivative, and that's why it's sometimes never converge when it comes to training a deep neural network. And we do have this dropout, the regularizers that we talked about, which is basically a random array that we are generating using the NumPy random function. That's gonna, eventually during the training turn off these neurons randomly, so you can prevent the overlearning. Yes? Okay. Let me see the question. I think I didn't get what you said. Before taking your models, please can you tell me before how your models is taking the images? This is something we didn't clarify maybe. So the images basically in a computer are represented by matrices. So each index in that matrix is going to be the color is going to be the RGB representation of the colors. So from 0 to 255. And what we did basically, we converted that 255 to being a binary image. So it's going to be black and white. So the way we feed the image to the neural network is by converting it to a matrix first, and then you convert it to one feature vector to one vector that contains all the pixels. So we're gonna kind of flatten that matrix, so we'll be able to feed it in this input neurons that, as we said. I hope that answered the question, Riyadh. Okay, so after defining the activation functions that we're gonna have, let's now look at the plotting of the sigmoid. So this is how the sigmoid looks like, and people used to use it in all the cases, in the hidden layers, in the output layers and such. But it turns out that this, as you can see, this plot here, when the data goes from -4 and +4, the slope of the function actually tend to be very small. So the derivative of this function, when the data is bigger than 4, the slope is going to be very small, and this is actually what causes the problem of what is known as the gradient vanishing. So when it comes to training this deep neural network and you use a sigmoid function, it's going to actually kill that gradient, and your parameters, the connection between the different neurons, won't be optimized in the right way. And that's why people tend now to use the ReLU, which is named as the rectified linear unit. And you can see that this ReLU, its shape doesn't have the gradient vanishing problem. So there's no derivative that's equal to 0 here in this ReLU basic plot. And that's the reason why we're using the two. And one intuitive question would be like, why we don't just use the ReLU for the output, and why we're using it just in the hidden states. And because the ReLU does not scale your data between 0 and 1, and that's actually why we use the sigmoid, because it's going to eventually, since we are using the cross entropy loss, so we want to produce a probability in the end, and that's why we put the sigmoid just at the end. So let's now define the hyperparameters of our baseline. So we're going to start by the input neurons. We saw the picture contains this number of pixels, so we're going to set the input as being this. The hidden neurons, we're going to set them as being 100. And to be honest, like if you want to define the input neurons and the output neurons are basically according to your data. But when it comes to the number of layers and when it comes to the number of neurons in each layer, there's no general rule on how to define these. You're going to eventually try a bunch of numbers and see which one works best. We do have the alpha, the learning rate, the iterations, and we do have the batch size. And this is something we didn't talk about yet, which is basically what we did in the linear regression model. We passed our data, all of our data in one iteration. We optimized that loss, and then we updated our model. And when it comes to training neural network, actually it's better to do it in batches. So instead of in one iteration you pass all your data, you're going to pass just a small batch of it, optimize it, and optimize your model and pass the second batch. And this actually has two reasons. So the theoretic reason of it is when you have these small batches, it's going to be easier to optimize that loss function. And the practical reason, or the practical reason will be that if you have many batches, actually you can eventually parallelize this computation and you can eventually gain more training time. So this is basically the intuition behind the batching. Let's now define the prediction function. So basically the function of our neural network. So it's going to take an image as an input. It's going to take the weights between the input and the hidden, and the weights between the hidden and the output as a matrices. So basically it's going to do is going to read the image. It's going to activate ReLU based on the dot product between the input multiplied, so the image multiplied by our weights, by our synapse. The output layer is going to be the same thing. So it's going to be the dot product between layer 1, so the hidden layer, and the weights on the between it and the next layer. And in the end, we're going to just apply the sigmoid that we talked about on the output layer. So we talked about cross entropy. So this is its formula, basically. So this is how you define the difference between the probability distribution. So it's going to be the y, your prediction. So the negative mean of the y multiplied by the log of the predicted y. If you define it by code, so this is the mean square error that we talked about before. If you want to define it, you're gonna just call this numpy.mean function with a negative, of course, and you're gonna pass basically the labels that you are training and the actual output that you have. Okay, let's define these. And here we are basically defining the weights, so those matrices between each layer. And we're gonna use this random function that's gonna generate random number for us. So we saw in the linear regression, basically we defined them as 0, but that turns out to be a very bad practice when it comes to training these networks. You want to always to define them as being random. And there's actually a lot of theory behind this. Certain people are working on it. Actually, there is an active area of research of it. And basically what they do, they see which distribution you should sample your weights from, so you will have an optimal learning experience when it comes to the training. So let's define our weights. And let's first test our model without training it. Let's see what it gets, like that random guess, and what does it look like. So let's pick an image from our data set, the index number 25, and it's a 3 as we plot it here. And let's run a prediction. So basically we call the predict function, we give it the images, and we give our weights as well. And this MP argmax is gonna basically, because we're gonna have a vector that contains probabilities, and the argmax is gonna give us the index of the highest probability, and that's the prediction that we think is correct. Okay, just a second. Oh, ReLU is not defined. I think we forgot to run this one. Okay. Hello. Yep, sure, go ahead. Oops, sorry. Yeah. That's actually a totally random choice. So as we said, we want our weights to be as stochastic as possible. So there's no intuition behind that. It's totally random. But when it comes to practice, and when you use like frameworks like TensorFlow, Keras, and such, they do sample from. It's not just random. They do sample from certain distributions that gonna eventually give you an optimal learning experience. No, I think not. I think not. So for me, I just started by setting them as random, and I just multiplied them by 0, and this actually gave me a better performance when I was building this model. So for me, there is no intuition behind this. So when it comes to practice, yes, you want to sample from from a certain distributions and such, but this is totally random. Welcome. Okay, so let's run our prediction function with those random weights that we had. So you're gonna see that our model is predicting this picture as being 1, when in fact it is 3. So it is completely a random guess. So let's try to pick another image. Let's say let's pick number 28. Let's say we're gonna plot it. So you can see that this is a 9, and let's run our prediction, random prediction with this image. Let's see what our model guessed. So this model thought that this 9 is 6. So this is just to show you that this is completely like a random guess before we launch the training. So when it comes to the training, this is the code that we have, which consists basically on 3 parts. You have the feed forward, so the forward pass that we talked about. You have the backward pass, and you have the loss that you are calculating. So you're gonna make a for loop through the iterations, and you make another for loop, explicit for loop, to run through the batches and the data that you have. So you're gonna start by the feed forward that we defined before. So take an image, apply the ReLU, the dot, multiplied by the input and the weights, apply the dropout mask that we talked about, and then you're gonna take from that previous layer and apply the sigmoid function on it, and that's gonna give you the output layer, which is that random guess. You're gonna call the cross entropy loss, where you're gonna calculate the difference between the output and the actual label, and we're gonna accumulate it here in the error variable, and then we're gonna launch the back propagation for our batches. So in this first line here, we are basically calculating the accuracy. So we are checking which checking which predictions this network got it right, and accumulate it here in this variable. Here we start calculating the derivatives. So we start from the end of the network. So we're going to use this Sigmoid prime. We're going to give the labels and subtract them from the output that we have and divide them by the batch size. And then we're going to back propagate that gradient through the network that we have. So this is what we are doing basically here. So you're going to call this layer 1 delta, so the layer 1 prime that you have, and it's going to be the layer output delta. So this one dots, so multiplied by the weights that we have transposed, and we transpose our weights matrix so we can allow that multiplications, because we are going backwards, so we have to transform our matrices that we have, and we're gonna multiply it by the ReLU prime that we had in the first layer, multiplied by layer 1. Here we're applying the dropout mask too, so we did apply the dropout in the forward pass, and we're gonna apply it in the backward pass as well. And after calculating this derivative, these gradients, you're gonna want to update your weights, where you're gonna, the weights from 1 to 2 is gonna be the 1 to 2 plus the alpha learning rate multiplied by the gradient that we have. And for the second matrix of the weights is gonna be the same thing. And then eventually, this is just an if statement, so we can plot our accuracy while our model is training. So let's try to run this piece of code. So you can see in the iteration, so you can see in the iteration number 0, the accuracy was about 13%, which is basically very poor. And as you train, the accuracy is gonna get better and better. So 10 iterations, 76%, 81, and it's getting better for the predictions. So during this training, do you guys have any questions that you want to talk about? If you have any questions, just feel free to leave them on the chat, or you can just activate your mic and ask us. So as you can see, the accuracy is getting better after each iteration. Yep. Yeah. I see your point. I see your point. I totally see your point. And this is the point that Pedro Evangelista mentioned before, where the number of iterations matters. So for this case, I just defined the number of iteration, which works best. So I start by defining it as being, I think, 10,000, and I saw that the learning is getting better, and it reached 95%, I think, and then it will drop. So that's how I defined my number of iteration. This is exactly what you want to do in practice. So try just a bunch of numbers, and you're gonna eventually, get that intuition from the result that you want to get during the training. So after 100 iteration, we did get 89% accuracy, and you see that so we are printing our weights. So our weights changed accordingly and according to the gradient that we updated by. So after the training, let's now make another prediction using this trained model. So let's read an image, and here we are reading an image from the test images instead of the actual training set that we looked at. So this image, we can see that it is a 5, and let's run our model using this 5 and giving it the trained weight. Let's see what it's gonna get. So you can see it got a 5, a correct label. That's to prove that our network actually learned the pattern behind these 5. So let's try another one, for example. So this is a 3. Let's see what it gets. And it got a 5. So you can see that the pattern of this 3 is actually too complicated. So in order to get a better accuracy for this 3, you're gonna have to tweak your model more and optimize your hyperparameters and train your model more to get more accuracy in your model. Let's try another image. So this is number 0. Let's see what our model will get. It's gonna get a 5 to, oh, we are making a mistake here. So you could, yeah. Good question. So we talked about the baseline and how we can define it. So in the linear regression, it's gonna be eventually, based on how complex your data is. But as I said, there is no clear way, or there's no rule on how to define the number of neurons and the number of hidden layers, basically. So it's gonna be an intuitive thing. So you look at our data and how many abstractions you need and how complex your data is, and that's how you're gonna train. Try with one layer certain neurons, and if it didn't work, you increase it, decrease it, and that's basically, so it's an empirical process, basically. So try something, if it didn't work, tweak it, and that's how the machine learning process goes. So we can see that the prediction was right here. So it predicts that this one is 0. So yeah, congratulations. This is the first neural networks that was trained on predicting the handwritten digits based on an image. Before we go though, I just want to show you this simple code that was implemented using Keras. Keras is a high-level API based on TensorFlow, one of the famous frameworks when it comes to deep learning. And you can see that using a high-level framework, you can define a neural network in basically 3 lines of code. So everything is pre-built. All of those functions, all of those updates are pre-built into these functions that we call. So you're gonna create sequential model, add your layers, add the hidden layer, and add the output layer. And then we are printing the summary. And then you're gonna give it the cross entropy loss that we defined, give the optimizer, and everything is predefined. You just need to tell it what you want it to use. And if we run this model, it's going to actually converge in the same way. And the best thing about these high-level APIs is that they do have a lot of pre-built things. So it's going to save you a lot of time. And when it comes to deploying these models, they actually provide you a lot of tools. They give you Docker images ready for the models. They give you APIs open and all of that. So in our example, for learning purposes, we just implemented it using NumPy, so just basic numerical computation library. But this one is a high-level API, which everything is pre-built in it. And you can see that this model got 83 accuracy, about the same thing that we did get. So this was neural network. Now we're gonna talk about the, let's go back into the slides. We're going to talk about that concept that we talked about in the plan of the workshop, which is called the bias versus variance trade-off, which is a very crucial point to understand when it comes to training and building these models. So before we jump into this point, is there any questions that you want to ask, guys? Yeah, definitely. Yeah. Yeah. That's definitely a valid point. So that depends purely on your implementation. So if, for example, if the code in the code that you get that I gave you, you can basically add the if statement in that code, and say, okay, if accuracy is equal to 95%, or depends on your threshold, you're gonna just break the training and save those weights. And when it comes to using high-level APIs like Keras, they do have this feature embedded actually. So you do have, after each 100 iteration, they do have checkpoints. So even if your model like converges and then go down, you can go back to that endpoint and take those parameters that was at that specific endpoint. I hope that answered your questions, Riyad. Definitely. Definitely. You can put the checkpoints. You can store those arrays that we had, those parameters, in another array at each checkpoint. But that actually will consume a lot of memory for us, because you're gonna have if you have 1,000 iteration, you're gonna have, if you have 1,000 checkpoint, you're gonna need a lot of space to store those matrices. So that's why we didn't do it. But it's definitely a good implementation and a good strategy to do. Okay, any other questions before we move to the bias variance trade-off? Do you want to answer that question, or should I? Yeah, yeah. That's actually a very good point that they asked, where people need to understand that machine learning is not just about implementing these small codes and understanding theory and implementing it. It's actually related toward software engineering and understanding the machine learning engineering pipeline behind it. That's actually a very crucial point to understand. Okay, so let's now talk about the bias variance trade-off that we did talk about, which is a very crucial point when it comes to implementing and understanding these models. So what we've done so far in the models that we talked about, the linear regression and the artificial neural networks, basically what we did, we were aiming at reducing the training loss or the error loss. But how can we relate that to the testing error? Can we know that, if we give our model a novel data, can we know that the training error is going to be the same as the testing error? And that's what the bias versus variance trade-off is all about. So we can express the testing error as this mathematical annotation. So you're going to consider the testing error as being a random variable, and you're going to define it as being the expected value of this random variable, which is just the Euclidean distance between the hypothesis, taking the x, producing the y hat, and you subtract it from the actual y that you have, and you square it basically to calculate the distance. And it turns out, after applying a bunch of deductions on this specific term here, you're going to end up with this very crucial three terms here. So let's talk about them here now. So the testing error, or the expected test error, can be decomposed to these three terms. And let's start by the bias. So we have the bias here, that it is the expected x of the y hat subtracted from the y hat. And the y hat basically here define the average classifier. So you take a certain baseline, you take a linear regression, and let's say you train it in such a perfect way that you get this you get the expected you get the expected hypothesis. So it's defined as y hat. And this term here represents that perfect model subtracted from the actual model. So even if you have you have linear regression and you train it on a perfect training strategy, you're gonna still have this term here. So this one represents the bias. And you have the variance here. So this is the variance of the model. So this was the bias. This is the variance of the model, which represents the training hypothesis, so the one that we did train, subtracted from the actual hypothesis. So this has nothing to do with the data, so it doesn't matter the data here. We are just subtracting two hypotheses. And one point that I want to add about the variance is as you can see, this is the definition of variance for any given variable. So if you subtract any variable from the mean of the data that it's in, that represents the variance. And we do have the noise. So the expected test error is the variance of the model, the bias of the model, and the noise of the data. And this has nothing to do with the model. This is just the data. So a good example for this will be, for example, the housing price data set. For example, you have a certain house with the same features, but in our data set has different prices. And that's something that you cannot overcome using the models. So you can just perform some data cleaning or outliers detection on your data. Okay, let's now try to visualize things and how they look like when you with a given example. So imagine that this is a panel that you are shooting at using certain arrows, and this is the four cases of variance and bias. So let's start by the first case, when you have you have low variance and you have low bias. So your predictions or your shots on the panel are going to be very accurate just in the middle. So this is the best case. This is the case that we always hope for. And you have a certain fluctuation here, maybe due to the noise of the data. So that's something that you can overcome by tweaking the data and not the model. We do have the case here that it is high variance and low bias. So your model is actually systematically correct. So it is hitting the center sometimes, but it is varying a lot, and that's what the variance means. It is varying in its prediction a lot, and that's what summarizes here this picture, this case here. And we do have the case which is the high bias and low variance. So as you can see that your predictions are actually very correct at hitting the certain points. They are not varying a lot, but they are missing the center. They have a systematic error. So yeah, they are missing the center completely. And when it comes to the worst case here, so the high variance and high bias, we're gonna your predictions are gonna be missing the center completely, and even if in that miss they are varying a lot, so your model here is completely misguided. Okay, an intuitive question here would be that okay, if we do have if we can decompose this error to these three terms, why we just work on reducing or optimizing these three terms? And it turns out that this is just a mathematical explanation or a mathematical decomposition of these errors. So during building these machine learning models, you cannot actually access these terms. So you cannot say, okay, the distance is equal to 20 and part of it is variance and part of it is bias. That's not something that you can do. But what you can do, and what we will see in the next slide, is trying to observe certain symptoms that your models show during the training, and that's how you know that, okay, your error is due to the bias or your error is due to the variance. And this is basically summarizes that. So when you have a high variance, or what is called the overfitting, the symptoms of that one is going to be that the training error is much lower than the testing error. So when you train your model during the training, you're getting an amazing accuracy, but when it comes to the testing error, your model won't be able to generalize to that new novel data, and that's the overfitting problem, and that's where you're going to use things like regularizers and such. So another symptoms will be that the training error is lower than the desired error threshold. So that's where we need the threshold that Riyadh was asking. So you define a certain threshold, and actually you don't want your model to go over that threshold. You just want it to be at that threshold. And if you have a variance problem, so if your model is not able to generalize to the new testing data set, the remedies for that, or how you can recover from that, is basically add more training data. So you need to train your model on more data so you can eventually generalize. You may want to reduce the model complexity, so you want to reduce neurons or reduce certain variables and such. You want to add regularizers. For example, you want to add dropout or the L2 norms and such, and this is what the regularizers is meant for, is to push or allow your model to generalize better. And you can use this strategy, what is called the bagging, where basically you're going to train the same model, you're going to train it on different parts of the data set, and then you're going to average those models together. And this turns out to be a very good practice when it comes to reducing the variance problem. So about the bias, the underfitting. So this is when your model is not fitting even the training set. So even during the training, the model is not fitting that data set. That's how you know that your error, or most of your error, is consisting of the bias problem. So the symptoms will be training error is higher than this desired output. And if you want to solve this or reduce this term, you're basically going to add more complexity to your model. So if you have linear regression and you're using just 2 parameters and your model is not fitting, you might want to add more parameters or add more features, as we're saying here. If you have a neural network, you may want to add more neurons and more layers and such. And this is actually very crucial. These two differences are very crucial to understand when it comes to training these models, because sometimes you see certain people, they are training this model and they do have, for example, bias problem, and they apply a bunch of remedies for the variance, and that's actually going to even inflate your error more and make it worse. So this is the last point that we want to talk about in this workshop. In this next slide, we're just going to provide a bunch of learning resources so you can dive deeper into each of the components that we talked about in machine learning. So when it comes to loss functions, if you want to compare between the geometric loss function, the Euclidean distance, when we should use it, when we shouldn't. When it comes to optimization, when it comes to, for example, the cross entropy, the probabilistic loss function, this article here summarizes all of those, and it gives you actually good insights when we should use each one of them. When it comes to optimization, we said that optimization is coming purely from math. So they are basically, it's a math field, basically. But I found this chapter from the deep learning textbook by Ian Goodfellow. It is very informative, actually. It has, it summarizes all the optimization that you might need when it comes to training these machine learning models. Evaluation metrics, when you should use recall, when you should use loss, errors, and such. This article, it's a tour that gives you the difference between all of those. When it comes to regularization that we talked about, the dropout, L1, L2 toms, the bagging, the chapter 7 from the deep learning textbook actually does exactly that. So when it comes to, so this is the other components of machine learning pipeline. When it comes to building models, so if you want to choose, if you want to do linear regression, SVM, neural networks and such, there are these 3 courses that you can take, and they are available basically for free. You have the machine learning course by Andrew Ng, which takes you into some of the examples of machine learning models and such. When it comes to deep learning and artificial neural networks, there is this specialization at Coursera, which is, you can just apply for financial aid and you will get it for free, which takes you into all the architectures of neural networks and how they work. But Coursera courses tend to be very small and very short, and sometimes they do skip certain details. So if you want to get full details about the things that we talked about, I would highly recommend you to check this course by Cornell University, which is about 34 lectures long, but it does, touches every nerdy, dirty detail of the machine learning. When it comes to the bias variance trade-off, if you want to understand how we did decompose that expected label into those 3 terms, watch this lecture from Cornell University too, and it's going to explain the math theorem behind it. The mathematical recap, if you saw that the things that we talked about mathematically were a bit complicated for you, you definitely want to check the deep learning textbook, the part 1. So they do, teach you all the things that you need for tackling machine learning and tackling deep learning. They're going to take you into linear algebra, optimization, numerical computation and such. And when it comes to reinforcement learning, so the study of agents and building artificial agents and such, there is actually a whole textbook for it named by the reinforcement learning textbook, which was written by Richard Sutton in Alberta University. So let's make a quick recap about what we did in this workshop. So we did define the machine learning and the different components of it. We did talk about the types of the models and how they are categorized and how they do overlap between each other. We did see 2 examples of models. So we did see a linear regression model and an artificial neural network. And then in the end, we talked about the bias variance trade-off and why you should understand it when it comes to training these models. And in the end, we just saw these learning resources that you can use to dive deeper into machine learning and deep learning. So yeah, so that's it for this workshop.